Hello, my name is Dalton Perry. Today I'm going to be talking about offshore wind energy. Am I serious? Okay. Hello, my name is Dalton Perry. Today I'm going to be talking about offshore wind energy. Now, for context, we as a global community are going to be facing serious problems surrounding anthropogenic climate change. One of the largest contributors to this problem is greenhouse gas emissions produced by our energy industry, which is primarily dependent on fossil fuels. And even if we could just wave a magic wand and make climate change disappear tomorrow, fossil fuels themselves are inherently finite. And it's for these two reasons that in the coming decades we can expect to see a transition from fossil fuel dependent energy to more environmentally responsible, renewable energy sources. And in fact, several countries, the United States included, have committed to reaching net zero greenhouse gas emissions by 2050. Now, wind energy is fast growing and very promising, which makes it a good candidate to make up a large part of the energy industry after we make that transition. Today we're going to be talking about whether it makes sense to invest in wind energy now, and if so, what type of wind energy to invest in. Now, the scope of this conversation is going to include your standard onshore wind farm, which you're used to seeing, your deep water wind farm, which is built on floating platforms, and shallow water wind farms, which are fixed structures that rest on the seafloor itself. And we're going to be evaluating these today according to three criteria: the environmental impact, economic feasibility, and proximity to energy demand. Now, the first criterion we're going to talk about is environmental impact, and this makes a lot of sense to consider because environmental responsibility is one of the primary motivators for building and investing in wind energy. So if we had a wind turbine that was environmentally harmful, that would sort of defeat the purpose, right? So environmental impact is a broad and complex issue. For simplicity's sake, we've narrowed it down to two main metrics that we're going to look at. And the first is CO2 payback time, or the time it takes for that turbine to make up for the greenhouse gas emissions associated with its own construction. So going from left to right, we have onshore performing the best for CO2 payback time, shallow water wind farms performing the worst, and deep water coming in second place. Our other metric is ozone depletion, or other non-greenhouse active pollutants associated with the turbine's construction that contributes to the depletion of the ozone layer. And again, in this metric, onshore wind farms perform the best, and shallow water and deep water have flip-flopped, with deep water performing the worst and shallow performing second best. Overall, onshore has an advantage environmentally. So next is economic feasibility, which we're going to primarily discuss in terms of cost. So we've got a graphic here with investment costs on the y-axis and cumulative capacity installed on the x-axis. And what we want to notice is here plotted in red, we have investment costs for onshore wind, and we notice that it drops over time, especially once we reach about 10 gigawatts of installed capacity. And in blue, we have offshore wind investment costs plotted with cumulative capacity installed, and we have not yet observed that same drop in investment costs. And because of that, there's a lot of uncertainty as to whether offshore wind can become competitive with onshore wind in that regard. In addition to that, floating platforms have an additional economic advantage in that they're more expensive to construct, more expensive to maintain, and more expensive to decommission compared to fixed structure, shallow water offshore wind farms. So moving on to proximity to energy demands, we have a heat map here generated by the National Renewable Energy Laboratory, showing wind power class, with red and blue being class 6 and class 7, yellow and pink and magenta being class 3, 4, and 5. So going from east to west, on the east coast, you generally have shallower waters, which lets you build the less expensive fixed platform wind farms. You also have high populations and high energy demands, and these proximal high power class wind resources just offshore. So moving west, in the Midwest, we have generally lower wind power classes, usually 3 and 4, and the Midwest is more sparsely populated, and with the exception of like Chicago and the Dallas area, less energy demand overall. And coming over to the West Coast, you have generally deep waters, and you're looking at constructing the more expensive floating platforms, as well as high population, high energy demand, and these very high power class, large wind resources just offshore. And it's at this point that offshore wind starts to make sense. Even though onshore wind has a small advantage environmentally and a considerable advantage in terms of investment costs and operation costs, if you want wind energy on the East Coast, your only option is shallow water wind farms. And if you want wind energy off the West Coast, your only option is deep water floating platform wind farms. So, to summarize, environmental impact between them all, onshore wind has an advantage, but because they're displacing fossil fuels, relative to that environmental impact, the offshore wind and onshore wind farms have a minuscule impact overall. So that's not going to be a deciding factor between these. And economically, offshore wind remains uncertain, and in addition to that uncertainty, floating platform deepwater wind farms have higher costs compared to shallow. And coastal areas have these huge wind resources very, very close to their large populations with high energy demands. And it's for these reasons that we conclude that it makes sense to develop offshore wind in shallow waters, especially off of the east coast of the United States. Thank you for watching.